Okay, so sorry, this is the 10th day or something, and I'm sure you're very, very tired. So I'll try to keep it very, very simple. So I will just sketch some things and so on, and you can find more details in some references which I can give you if you're interested. Okay, so I have two problems that I want to describe to you. I don't have to do all two of them, so I'll just do one, and then depending on time and how many of you are sleepy and so on, I'll go or stop. So I don't mind. Okay, fine. So, so I wanted to speak to you about fixation probability in static and dynamic environments. So thanks to Lindy, all of us are experts on fixation probability. Everybody knows what fixation probability is? Good. Okay, so I don't have to say that much. But can somebody tell me, why are we interested in it? So what I'm thinking about is the following. I have a population, which is sort of large perhaps, and it's a wild type population. Maybe all individuals have the same sequence. That means it's a monomorphic population. Or maybe there's a distribution. That means some organisms, some individuals have 3 mutations, some have 5, and so on. There's a distribution. And then a single beneficial mutant comes. And we have been asking, what's the chance that it fixes? Why? Why are you so obsessed with this p-fix? Okay, so I think Lindy was planning to do it, but maybe she'll do it today. So I'll do it today for you. She'll do it tomorrow. Okay, so I'll illustrate that using a simple thing, a simple model. And I will describe some results in 2 settings. One is when the environment is static, and when the environment is also changing, with some in certain way. So let me first do the intro part. Okay, so the first problem. Okay, so I'm looking at a large population, and this is the allele frequency, which I denote by x as a function of time. And I am thinking of a population in which all the organisms, all the individuals have the same genome. This is a monomorphic population. So, frequency, it cannot exceed 1, right? So all of them have the same frequency. So this frequency doesn't change. Nothing happens to it for some time. But then one beneficial mutation comes along. It happens to arise. And then as a result of that, the frequency of the beneficial mutant rises and of the original population drops. Okay, and so this drops again, and yet another beneficial mutation arose, and its allele frequency rose, and so on. Is it clear what I'm saying? Right? So, an innovation happened here, so that took over the population, then another innovation, and so on. And this is a standard question in adaptation, which is, what's the rate at which these beneficial mutations are fixing? What's the rate of adaptive substitutions? So in this case, so suppose I have some Tmax here, let's say 100. So there are 3 of them which has happened. So I would say the rate of adaptive substitutions, which is generally denoted as EKB, is 3 by 100. Okay? But let's now, don't put specific numbers, but could you tell me how to calculate it? I mean, it looks like an easy question, right? Because what you have is n individuals, and let's say the rate at which beneficial mutation arises is UB. So there are n individuals. Each of them per unit time produces a beneficial mutation at a rate UB. So, they arose and fixed. That's it. Hey guys, you're disappointing me. Right? Is it okay? Really? No, come on. Right? It's not okay. Why? Because it's a finite population. You can't just come and win. There's a stochasticity. And that's why we don't see those little changes here. Let me draw them. So what could have happened is, another one arose here, a beneficial mutation, but it got lost, right? So I won't see them, right, when I'm seeing these large frequencies. So therefore, I have to put in this factor called fixation probability. These are the ones which were produced per generation. That means the pink one was also produced, but I have to account for that it was produced but got lost, right? So therefore, what I should do is to write the production rate into Pfix. Okay? So in this case, you know, already you've heard it yesterday and today. So in this case, it's simply 2 times the fitness advantage, let's say is SB. So it says 2 times SB. Okay? The key point I wanted to make here is that you need the fixation probability to build these stochastic models. Evolution is a stochastic process in most realistic situations. And therefore, to account for the stochasticity, this is the deterministic part, and this is the stochastic part. So you do need this. So we better learn. Okay. So fine. Now let's stick with this picture for a second. What do you think is wrong with this? There was something wrong, right? I didn't draw this pink guys, which were getting lost. There's still something, a lot of things which are wrong with it. Any ideas? It's a big word. Yes? Yeah, that's one thing. Yeah, so clonal interference could have happened because you see, okay, so this is another beneficial mutation. While this was going to fixation, this one arose and oops, it rose almost there, but then this one, you know, I didn't draw it correctly actually, but you know, it got lost because this better one came by. So maybe, okay, but I think you'll hear about it tomorrow. So that's one, but that's again about beneficial mutations, right? What else is wrong with this? Yeah, deleterious mutations, right? Nobody thinks of the bad guys, everybody thinks of the good guys, right? So what about the deleterious mutations? They must have also arisen. We only spoke about UB, that is the beneficial mutation rate. There is a UD, which is in fact much, much larger than UB. So these individuals would also be suffering with deleterious mutations. So therefore, this rate of substitution would be affected by the deleterious mutation rate, right? So therefore, that's another factor which I haven't taken care of. But in general, you will have both beneficial mutations as well as deleterious ones, which would affect this quantity. So I'll focus only on one part because you'll hear about clonal interference tomorrow, I think. Yeah? And I'll speak only about the effect of deleterious mutations. And when you have both of them, I'll give you a reference by paper, which you can read. Okay. So let's include deleterious mutations. So that was intro. Okay. So now I don't want to think about a monomorphic population. Let's forget beneficial mutations for a second. So I have this population which is you know, quite well adapted, or okay, it's not well adapted, it is some population of size n, okay, and you know, there's an onslaught of deleterious mutations which was going to decrease its fitness, okay, and each deleterious mutation decreases the fitness by a same factor 1 minus SD. So let me write down this model a little bit for you. So I'm again thinking of a large population, size n, okay, and in this population, deleterious mutations occur at a rate UD, and each deleterious mutation decreases the fitness by factor 1 minus SD. So this is the you know, fitness reduction per mutation. That means I'm saying as a factor, so I'm ignoring epistasis, not because it's unimportant, but because it's simple, and some of these things are easily generalizable, but I will not do that. Okay, so I'm going to ignore epistasis. Okay. Okay, so let's just look at this population for a second without any beneficial mutations. And I would like your input. So I want to plot the number of deleterious mutations on the x-axis and frequency of individuals which have such k deleterious mutations. Let's call it k. Do you understand the question? So I'm saying some individuals have 5 deleterious mutations, some have 10, some have 9, and so on. right? So what do you think this distribution would look like? Any idea? Decreasing, okay, it's possible, yeah. Why is that? Why is it decreasing? Could it be an increasing function? No, because so you expect that there cannot be too many deleterious mutations, right? Because if it has too many deleterious mutations, it is really unfit guy. So selection is going to purge them, right? So therefore, there's nobody here, right? On the other hand, generally, very likely, there are very few or no individuals which are deleterious mutation free, right? Okay, so you expect something like this. So there will be some few individuals with one deleterious mutation and so on because there is mutation. So this is due to mutation. And this part, that there's nobody here, is due to selection, negative selection, right? So it's something like this. Some distribution of this kind, right? Okay, so the shape of this distribution is a classic result in the subject, and it's a known distribution. It's a Poisson distribution whose mean is given by UD by ST. So it's a very simple, nice result. Okay, so I'm assuming here n is very, very large. Okay, so it's a Poisson distribution. Okay, so now, I have this not a monomorphic population as I assumed here, but rather I have these individuals, some with 2 deleterious mutations, some with 3, 4, so on and so on, and so forth, right? But most individuals, depending on these parameters, have this UD by SD deleterious mutations. Setting is clear? Okay. So now a beneficial mutation comes along, okay? And I want to know what's the chance it fixes when I have this kind of population. Okay. Yeah? Yeah? Yes, yeah. Yeah, so I didn't use this word. So this is the population mutation selection balance. Yeah. Yeah. So I should just say. So because we didn't use this word in this course, I think, or equilibrium. Yeah. Mutation selection balance, yeah. Yeah, okay. Okay? Yeah, okay. Okay, so now, there are no individuals with, let's say, it's 10. There are no individuals with more than 10 deleterious mutations, say, right? So now, if the beneficial mutation comes, it has to come in a background in the individuals that have maybe 2, 3. So let's say it starts over here. Change that a bit. So it has to come into individuals which have 2, 3, and up to 10 deleterious mutations, right? Okay, right? So I'm going to call this number because it's going to be important. So number in which beneficial mutation can arise, this number, arrival 1, I'm going to call it UD by ST. So just remember this. This is analog, somewhat analog, I mean, it's not exactly the same thing. It's analogous to this number, that it can arrive, how many are there, right? So it's something like that. So this is the arrival part. But just because I have arrived doesn't mean I will win the game, right? So in any genetic background, beneficial mutation can arise, but it may not survive. So I have to say something about the genetic backgrounds or the number of deleterious mutations in which it can survive. Do you think it can survive if it arises here? Individuals of this kind? Yeah, so we'll fix it, yeah, that's right, yeah. So it has to be super beneficial, but we fix that. So, you'd think that somewhere here, if it is, it might survive. But we want to say something more quantitative about that. Okay, so let me take you through this argument. And it's actually coming from branching process. So let me just explain that anyway. Okay, so we have these individuals and a beneficial mutation is going to come. Would it spread or not? In which genetic background it would survive? Let me give a very simple argument for that. If it's going to spread, then what's the simple thing that you can think of? If it's going to spread, right, then the fitness of the new population must be larger than the fitness without the beneficial mutation, right? Right? That makes sense? So the fitness new should be larger than fitness old. Yeah, large populations, yes. Yeah? Hmm? Okay. So there is, by old I mean this population. It has some formula. Don't worry about that. Okay? Now this beneficial mutation, let's say it arose, say over here, in individuals which had some deleterious mutations, and then all the progeny, they all had this beneficial mutation as well as deleterious mutations. Does that make sense? Because the ones which have, these ones, if it's a one-way mutation, each of them will carry at least deleterious mutations as well as the beneficial one. Okay? So W new would be enhanced or would be changed by this factor. Just have a look and see if it makes sense. Make sense? Right? So there is a factor which is going to increase the population's fitness because of beneficial mutation. But if it arises in a bad background, right, all of them are going to carry this bad deleterious mutation. That's going to decrease the fitness of the population. So it's a little tricky, right? So it cannot just arise in any random background. It has to have the right number of deleterious mutations, and this if you solve, okay, so you will see that I has to be less than or equal to SB by ST. Okay? Yeah? So therefore, the number of backgrounds in which it can survive, the maximum number is less than or equal to SB by ST. Okay, so let me just pause here. Okay, so I have two things here. This beneficial mutation can arise in individuals which have 5 deleterious mutations, but if what? Yeah, sorry. But it could survive, let's say, in only 3 of them. What do you think is the fixation probability? Would it survive? Would it, finally, will you see the beneficial mutation? So arrives in 10th one. Okay, let's say 7th one. But survival, that means it enhances the fitness only if it's less than 5. So would it survive? No, right? Okay. So let me just say that a bit more. So what I'm saying here is this. I have this genetic backgrounds, the distribution of genetic backgrounds in which it can arrive, right? Okay, so this is UD by ST, but survival could happen in over here. There's a number ST, SP by ST, right? So therefore, if it arises here, there's a non-zero fixation probability. Okay. On the other hand, right? So P fixed is 0 here, and it's non-zero here. So let me again plot P fix as a function of this parameter. I've written this parameter because I know the answer. But could you say, since you have been learning all these quantitative things, when do you think, how does this curve look like for fixation probability? Okay, so it's non-zero if UD by SB is less than SB by ST, right? That means if UD by SB is less than 1. So I don't know, maybe you understood everything and I'm just saying it again and again. Okay, so here is some fixation probability, I don't know what, okay? But above that, it's 0. Okay, So this is a sort of extreme case, what I have plotted here. But actually, if you do simulations and this branching process calculations, what one finds is that the fixation probability looks like this. It's very close to 2SB, when UD by SB very small, okay, and then it decreases like this. So it remains close to 2SB, and then it does this. So why I'm going through all this? The point is simply this. The first thing that I described to you, it says that the relevant genetic background is just one. There's very few genetic backgrounds, 1, 2, or so on, and so on, right? So there's a simple formula over there, which you can write in like 30 seconds. When you have SD by SB, that means the backgrounds in which survival can happen is more than one. It's largish. There are multiple backgrounds in which this could happen, and one can ask, I have lots of backgrounds in which mutant can arise and fix. So I thought that, there are several possibilities in which it can arise and fix. So maybe p-fix actually is larger than 2SB. But that's not the point, because it doesn't, survive in all of them. Okay? So therefore, one has to do some kind of weighting. There's a weight associated with each background, and one has to do some sort of small, calculation to see that. Okay? So a simple result I want to tell you is that when you have many genetic backgrounds present, unlike the first picture where there's only one genetic background, the answer looks like this one. And I'll just give you the expression just for completeness for the substitution rate. Okay, I'll just do that. So unlike that first one, okay, I'll write it here. So it looks like this. Divided by the object that we had there. Okay? So when I take the deleterious mutations into account, relative to the first answer, when there was a single genetic background, the answer is smaller, generally. Okay? So this just quantifies that how much substitution rate would decrease. Of course, understand it intuitively, right? Okay, so I just wanted to say that much. Okay, so this is okay? Okay, so there is some calculation and so on, but let me not say anything more than that. Okay, let me just talk a little bit about the second one. Okay, so this is okay, but this whole thing assumed that every time a deleterious mutation happened, it decreased by the same amount and so on, right? So some of you are asking, there's environments are never static. So then, how do things change? So it's a different model, and this is really work of Archana. So if you haven't visited her poster, you should do that. Okay. So now I'm going to give a quite different model, and it's slightly okay. So the first thing that I described to you, it uses branching process, okay, which I haven't shown in the calculation, but the blue curve comes from there, okay? And now I want to talk about static and dynamic environments where I use diffusion approximations, okay? So I'll again give you some simple answers here. So environment doesn't change, environment doesn't remain static. Can you give me an example of changing environments? Yeah, what else? But that's from Archana's poster. Anybody else? Can you give me a new example? Last week and this week, so different, no, environments. Yeah, so this is seasonal change, which is very periodic. What else? Active learning. Yeah, okay. But that's Vaishali's idea, right? Example. Huh? Just fluctuating, tick, 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 today, tomorrow, today I'm not feeling so great, tomorrow maybe better, and so on, right? So, okay, so there are these various different types, okay? And, there are these fluctuations. There are ones which is very periodic and, very deterministically changing environments, but typically they'll be both. So I'm going to describe to you a little bit about the case in which environment changes only deterministically and in a periodic fashion. So first of all, again, I want to ask you some things. Okay.
Maybe it's small already, but I just want to clarify is that.
Yeah, so so this back mutation, it's sort of like a back mutation then, which I'm not considering here.
Not a back mutation. I think it's in the branching process. You allow more deleterious
Yeah.
after the beneficial. Yeah. That is part of it.
Yes, so deleterious mutation rate is often larger, but then that would mean I should include what you are saying, right?
Yeah. I don't understand
So,
if that's part of it or not.
No, so I am not allowing them to go back, to include more ones. Oh, sorry. Yes, so once the beneficial mutation is fixed, that's it. I just look at that much.
But Deepa is asking en route to fixation.
Yes.
The beneficial one also.
Okay, en route?
Yes.
En route. Yes, that's included.
Okay.
So this hitchhiking is included. Yes, so it may arise with 7 deleterious mutations, but en route it may accumulate 8, 9, 10. So all that is included, yes. Thank you for clarifying. Okay, fine. Okay, so in 10 minutes, let's see. Okay, so I'm going to consider this periodically changing environment, and let me just plot that for a second, since you already know what S is. So it's something like this. Okay. So this is, somewhat slowly changing environment. Environment could also change fast. Right. So first of all, I want to ask you, if the environment was changing very, very fast, what do you think population would do? Meaning, what kind of selection would it see? Okay, fine. So for me, it took a while to figure out why. But, okay. Of course, you guys are smarter, so that's it. Okay. So what about the case it was going very slowly? What about that? Yeah, let me see. So it's changing very, very slowly. What's the first thing would you perhaps will think of? So environment, this is the selection coefficient I'm plotting here. Okay, environment is encoded, environment information, the selection coefficient. And it's changing very slowly. And then let's say a beneficial mutation is over here. Okay, so what do you think, what kind of environment would the population see now? An average environment? The local one, at that instant of time. Because it arose over here, right? If it's changing slowly enough. So we haven't spoken about this fixation times and so on. Okay, so there is a way to quantify how slow is slow. But if it arises and fixes before there's a change, substantial change, you expect that, if it arose over here, it is going to see this instantaneous environment. So this is the average versus instantaneous. Okay. So let's see. P fix versus, so I'm going to call rate of change as omega. So you told me when omega is small, it will see some instantaneous. So instantaneous means, suppose it had a fitness over here, or selection coefficient was SB, it will see 2SB, right? Okay? And at very large ones, it will see some average value, right? So suppose my environment is such that S of t is fluctuating about 0, right? So what's the average fixation probability then? The fixation probability in this average environment. Yeah. So it's about neutral value. I'm considering the average is 0. So amplitude is equal in both directions. Yeah? Okay. What happens in between? So you told me these 2 points, here and here. What happens in between? What do you think might happen? Would the fixation probability be large, small, same? What do you think? Maybe it's like this. Okay, so let's do it slowly. So it arose over here, and it hasn't really seen the negative cycle. Okay, selection coefficient is increasing, right? And omega is tiny, just tiny. Do you think it has a higher chance or lower chance or the same chance of fixing? So let's compare these two cases. So this value is SB. Okay. So this is the changing one, and this is the constant environment. So I'm not sure if you can see these differences. So this is, it remains as SB, same selection coefficient, and here it's changing slowly. So fixation probability is larger or smaller? Yeah, so it's over here. So this is S of t. I know let's not talk about times, just the chance of fixing. More or less? More? Yeah, I would also agree it's more, because when the environment changes slowly, selection is getting more and more. It's getting stronger and stronger, right? So therefore, it's easier and easier for the population to fix. So you expect that, okay, it to increase at very small omega, at very slow rates. If it's arising in the positive S cycle, yes, it's changing. No, it's more than that. I'm starting over here. I'm starting over here. Selection strength is increasing with time. So fixation probability would increase. Is it counterintuitive? Yes. The environment is changing continually. Yeah?
So you're saying there's one magical mutation which is beneficial across all these environments that are changing?
There's just a single locus which is under selection, and environment is changing slowly in one case, another case is changing fast. It's on the top part. So when S is positive, it's beneficial. And now strength is changing with time. So you expect fixation probability to increase. Is this okay? Or? Yeah? Okay. Yeah? Okay. So now we have to get over there, right? So you expect this to be something like this, right? Okay? This much is okay? Sort of. No? So there is some fixation, there is a rate at which the environment should change, at which the fixation probability is maximized. Okay? So from physics literature, I borrow this term called resonant frequency. The resonance with the natural frequency of the population and the driving frequency at which fixation probability is maximum. So I'll finish this because I just want to do a small part of it. Let's now take this other case in which, so S of t is doing this, but the beneficial mutation arose at this time. Okay? How does the prefix change? Does it not change? Yeah, sorry, I've been saying beneficial, I think, yeah, but it's a mutant. Yes, it arose at this time. Yeah, yeah. So omega versus prefix again. So it arose at this time. It has some S here. So it's probably 2S. If it is deleterious, it's actually not 2S. Sorry, let me just redo this part. Sorry. Yeah. Sorry. Let's not do this one. Let's do this one. It arose over here. How does P-fix, how might it look like compared to the first one? Yeah. This is S of t. So the omega equal to 0, what would be the fixation probability? 2S, right? Yeah. So this is the corresponding S. This is still SB. So this is 2SB, right? Instantaneous value. At large omega, tuck, 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 same, 1 by n, right? Okay. In between, yeah. Because very large, rapidly fluctuating, you see average environment. And I said S is on an average 0. Amplitude is same in both directions, so neutral on an average. Sorry? Oh, 2 because I was thinking of diploids. Oh, sorry, 2 factor, yeah, okay, 1 by n is fine. Yeah, actually I'm thinking of diploids, so 2. Yeah. Okay. So how does it look like now? Same? Same? Up and down? That's it? Yeah, down and up. Okay. Okay, sorry. Okay. Yeah? Yeah. No, so because that's what I try to argue here, right? That why is it decreasing here? So the reason it was increasing here is, now environment is changed slowly. Here, environment is again changed slowly, but S is decreasing. Yeah. Bump? No, because, so therefore, you have to argue here also. Yeah. So you wanted something like this? Yeah. Yeah, so that's one is slightly more involved argument, which I'm not giving now. Okay? And of course, we calculate, and it works. It's correct, whatever we get, I think. Yeah. Okay? So there's a minimum in the fixation probability. So if you drive it at that frequency and the time of origin, the time at which it arose, that is very important. These two, this guy and this guy, they look just opposite, right? The key point, one of the key points I want to make here is that when you have changing environments, the time at which the mutant arose, that is a key determinant of how your fixation probability would look. Okay? And you saw the diffusion approximation in the morning, that Fokker-Planck backward Fokker-Planck equation. Even at large times, the time derivative remains. Okay? So if you derive it the same way, okay, so you still have 2 time derivatives. One is the time at which fixation occurs, and there's a time derivative for the time at which the mutant arose. Okay, so at large times, one derivative goes away, but still you have a PDE. And that's what you have to work with if you're thinking of dynamic environments. Okay, so I think I should just stop here. There are other things and so on, but talk to me or Archana. Yeah. Yeah. Right. So on an average is flat. Yeah, that's right. But that's not what we are really interested in. We would be interested in something like rate of adaptive substitutions. So that's a slightly more non-linear thing, and I don't think this would be flat. Okay, so that's something which we haven't calculated. I don't know how to do it. But numerically, I think we will not see a flat thing. But what you're saying is right. If I integrated it over any origin time, it would be flat. Yeah. So I think I should just stop here.